Okay, let's unpack this. Imagine building a modern interactive web application, the whole front-end UI, using the exact same skills, libraries, language, basically C#, the stuff you use for your backend. That's the core idea of Blazor, right? Writing web front ends entirely in C#. And that's what we're diving into today, based on some great material from exploring Blazor, creating server-side and client-side applications in .NET 9.
Yeah, exactly. It's a really powerful premise. And Blazor, well, it actually delivers on it. It's a web UI framework that genuinely lets you use C# and, the whole .NET ecosystem right there on the front end.
Which is a big shift. I mean, traditionally, you'd need, what, JavaScript people for the front, C# people for the back?
Precisely. You often had specialized teams.
Mhm.
And Blazor's big promise, really, is the ability to consolidate that. You could still use JavaScript if you need to bridge something specific,
Yeah.
but that fundamental dependency, it's gone. It simplifies the whole full stack thing.
Okay. So our mission today is to really get into what makes this possible. We want to look at the architectural choices, those different rendering modes, and the coding basics that make Blazor, well, different. Right, so the first big question, C# is normally server-side. How on earth does it run securely, efficiently inside a user's browser? What's the magic here?
Well, the key technology is WebAssembly, or WASM. Our sources really highlight this. WASM lets languages like C# or C++A compile into this compact binary format that runs securely right there in the browser. It's the engine making it work.
Okay, WebAssembly, but what's the actual benefit for the developer beyond just getting to use C#?
Good question. The big thing with WASM is speed and security. It runs at near-native speeds. And critically, it runs in the same secure sandbox as JavaScript. So
Okay.
all those old worries about browser plugins, security holes, performance issues, they're just not there. You get C# power with web security.
That's a huge point. Okay, so syntax. If you've done .NET Web stuff, you've probably seen Razor syntax, mixing C# and HTML and .cshtml files. Blazor uses .razor files. Similar look, but you're saying the way they run is totally different.
Totally different, and this is absolutely key. Traditional Razor, the .cshtml pages, that C# code runs once on the server when the page loads. It spits out HTML. That's it. Static. But Blazor components, the .razor files, they're reactive. The C# code runs after the page loads, either in the browser via WASM or connected to the server. It responds to events like clicks or changes. And this means your loops, your if statements, all that C# logic inside the file. It gets reevaluated constantly based on what the user does. It enables real-time UI updates purely with C#.
Okay, that shift from static generation to dynamic event-driven, that's the core, isn't it? So how does Blazor handle that data flow, keeping the UI and the C# code in sync without, tons of manual JavaScript?
Right. It does this mainly through something called @bind. It provides two-way data binding, and it's pretty slick. You basically connect an HTML input, like a text box input type text or a dropdown, directly to a C# variable using @bind. Then the framework handles the sync, user types in the box. The C# variable updates, you change the variable in your C# code, boom, the text box updates on screen, almost automatic.
That two-way binding sounds convenient, almost too convenient. Coming from other frameworks, sometimes that magic causes performance issues or state gets messy. Is Blazor doing some heavy lifting behind the scenes, like constant checks?
That's a fair concern, but no, it's actually quite efficient. Blazor isn't using like constant dirty checking or heavy watchers. Instead, it relies on event notifications. When an event happens, a click, a key press that triggers a bind Blazor runs the C# logic needed. Then it does a very clever diff, comparing the old UI state to the new one in memory, and applies only the necessary changes to the actual browser DOM. It's very targeted.
Surgical, not broad.
Okay. And what about triggering more complex C# functions, like clicking a button needs to do more than just update a variable?
Oh yeah, super smooth. You use attributes directly on the HTML element, like at onClick, and point it right to a C# method in your component's code block. If that method needs data, or if you need to run, say, an async operation, you just wrap the call in a simple Lambda expression, like at my method, some value, or at async, await my async method. It lets you pass parameters cleanly and handle async stuff without any weird marshalling.
Right, so you can easily grab the specific input value from an event, not just the fact that something happened lets you go beyond simple binding if you need to.
Exactly. That detail matters. And, where that C# code actually runs, browser or server,
Yeah.
that completely changes the game. Which brings us nicely to those architectural choices, the 4 rendering modes you get with the newer Blazor web app template in .NET 9. And the first thing to say is there's no single best one. It totally depends on what your project needs: speed, offline capability, data access. Makes sense. Let's start with the one that feels most, well, Server-centric, server rendering.
Okay, server rendering. With this mode, all your UI logic, all the C# code runs on the server. Every interaction, every click, every key press gets sent back to the server over an active, always-on WebSocket connection. The server processes it and sends UI updates back. The huge advantage: you basically eliminate the need for separate web APIs for your front-end logic. You can just inject your database context, your services, directly into your Blazor components.
Yeah.
Super fast development for server-connected apps.
Instant access to server resources sounds amazing, but WebSockets, constant back and forth. I'm immediately thinking latency.
Yep, you nailed the trade-off. Server mode feels instantaneous if the connection is good, but every single interaction has to make that round trip. If the user's connection is slow or they're geographically far from the server, they will feel that lag. The app's responsiveness is tied directly to network quality.
Okay, so if latency is a potential killer, we look at client rendering, swapping network lag for what?
Exactly. Client rendering uses WebAssembly, so everything runs directly in the user's browser. Once it's loaded, interaction is incredibly fast, and it even works offline. This is great for things like, say, complex calculation tools, internal dashboards, apps where the user spends a lot of time interacting after the initial load. But there's an upfront cost. The browser has to download the .NET runtime and your application code first, so the initial load time can be longer.
And you lose that easy server access, right? If my client-side component needs data from the database, I'm back to building REST APIs or gRPC endpoints like any other front-end framework.
Precisely. You're making external calls, so it's perfect for presentation sites or self-contained tools, but less ideal if you need constant deep integration with server resources. And our sources also point out it's generally less SEO-friendly out of the box because search engines might not wait for the WASM to load and execute before indexing.
Which leads us to Blazor Auto, the hybrid approach trying to fix both the SEO and the initial load time issues.
Yeah, Blazor Auto is pretty clever. It starts by using server rendering for the very first page load. This means the user sees content immediately, search engines see content immediately, great first impression, good SEO. Then, while the user's looking at that server-rendered page, the browser quietly downloads the WebAssembly bundle in the background. Once it's ready, the app seamlessly switches over to client WASM rendering for all future interactions. You get that initial speed and the long-term responsiveness. Best of both worlds, kind of.
Smart. Okay, and the fourth mode, static rendering. Why have a Blazor component that just acts like plain HTML?
It's all about performance optimization. Think about parts of your page that are purely informational, like a header, a footer, maybe a static marketing panel. No interactivity, no changing data. You mark those components as static. Blazor just renders them as plain HTML on the server once. No WebSocket overhead, no WASM download needed for those parts. It lets you use the Blazor component model for organization, but ensures you're not paying a performance price for components that don't need dynamic capabilities. Just pure, fast HTML.
Got it. Efficiency where possible. All right, let's shift gears slightly to the building blocks themselves. Blazor is all about components, right? Modularity.
Absolutely. Components are central. They're those .razor files we talked about, acting like reusable custom HTML elements. You break down complex UIs into smaller, manageable, often reusable pieces. It's fundamental to how you structure a Blazor app.
And for a component to actually do anything useful, it often needs data from its parent. How does that data flow down?
That's done using parameters.
Yeah.
You define properties in your component's code block and decorate them with the parameter attribute. The parent component can then pass data into these parameters, just like setting attributes on an HTML tag. And these could be simple strings, numbers, dates, or even complex custom objects. That's how info gets passed down.
Okay, so data flows down via parameters. But what about communication up? If a child component needs to tell its parent something happened, like, hey, I was clicked, or the user selected this value, that often gets messy in UI frameworks.
Blazor has a standard way for that too, using something called event callback. The child component defines a parameter of type event callback, or event callback T, if it needs to send data back up. When the child wants to notify the parent, it just calls invoke async on that callback. The parent component, where it uses the child component, wires up that event callback to one of its own C# methods, so the signal travels cleanly back up the hierarchy.
Right, and combining those two parameters flowing down, event callbacks going up, that leads to this really powerful pattern for creating custom inputs, the custom two-way bind.
Yes. This is probably the key pattern for making truly reusable, complex components behave like simple inputs. Let's use that parent-child analogy again. The parent gives the child component some initial data, maybe a string value, that's the parameter. Let's call it example value. Now, inside the child component, maybe the user interacts with it, and that example value needs to change. How does the child tell the parent, hey, update your copy of example value? That's where the event callback comes in, but with a very specific naming convention. For Blazor's automatic @bind syntax to work, like @bind example value on the child component tag, the child component must provide two parameters. First, the value parameter itself. Parameter public string example value get set. Second, an event callback parameter named exactly the same but with changed added at the end. Parameter public event callback string example value changed get set.
Ah, okay. So it needs both example value and example value changed for the @bind example value magic to work automatically.
It's exactly. That strict naming convention is the signal to the Blazor framework. When the child component updates its internal value, it calls example value changed, invoke async new value. Blazor sees that, knows it's linked via the @bind syntax, and automatically updates the variable that was bound in the parent component. It makes custom components feel just like built-in HTML inputs.
That naming convention makes a lot more sense now. It's the handshake, basically. Okay, so let's pull this all together. What does this mean for developers? We've seen Blazor lets you use C# front to back using WebAssembly under the hood. We know the difference now between traditional Razor's one-shot rendering and Blazor's reactive event-driven updates. We've covered the architectural choices, server, client, the clever auto-hybrid, and static for efficiency. And we just touched on how components communicate using parameters down and event callbacks up, enabling that neat custom binding pattern. But there's one loose end. We talked about server rendering relying on that persistent WebSocket. If all the logic is running server-side over this live connection, what does that mean for things like security, authorization? It feels different from typical web apps.
That is the critical consideration the final thought developers need to grapple with, especially coming from other web paradigms. Because server rendering keeps the UI logic alive on the server through that WebSocket, the standard model of a client holding, say, a JWT bearer token and sending it with API calls, well, that model doesn't really apply in the same way. The API call is happening implicitly over the WebSocket connection to the server-side logic. So this reliance on the server maintaining the session state means you absolutely need robust state containers on the server. You need a secure, reliable way to manage per user, per session data, things like who is logged in, what are their roles, their specific authorization claims, and make sure that state is correctly associated with their WebSocket connection throughout its life. Securing a server-side Blazor app requires really careful thought about managing that state on the server, which is fundamentally different from how you'd secure a traditional client-side app that just calls stateless APIs.
So the architectural choice isn't just about performance or offline capability. It fundamentally shapes your security architecture, too. Understanding that need for solid server-side state containers seems absolutely vital if you're going deep with Blazor Server in .NET 9. A really powerful framework, but with its own unique considerations.